On a blackboard, a dense polynomial expression sits under the words Jacobian Conjecture. An AI cursor blinks beside it. Then a red X appears. The claim moving through the AI math world is not that a machine has delivered a verified proof. It is stranger and much more fragile. An AI-linked exchange may have pointed toward a possible counterexample, a mathematical object that, if real, would force people to rethink a problem that has resisted attack for roughly 90 years. That distinction matters. In mathematics, a dramatic output from a model is not a result. A chatlog is not a theorem. A viral breakdown is not verification. The only thing that counts is whether the construction survives exact checking by people who know where errors hide, and that is why this moment feels unusual. Recent AI math videos have started breaking out, not because every claim is true, but because the boundary feels different now. Viewers have seen careful hand checks. They have seen GPT conversations picked apart line by line, but taken together, those moments raise a sharper question. Did AI actually crack a 90-year problem, or did it do something almost as unsettling? Did it produce a lead strange enough that humans had to stop, look closely, and begin checking it by hand? For now, the responsible answer is uncertain. No proof, no disproof, no victory lap. Just a suspicious line on the board, and a problem old enough to make that suspicion matter. To understand why this story has gravity, we have to slow down and ask what the Jacobian conjecture is actually about, not in the full technical language mathematicians use, but in the simplest shape we can responsibly give it. Imagine a machine that takes points in space and moves them around. A point goes in, a new point comes out. If you feed in an entire grid, the machine may stretch it, twist it, bend it, or slide different regions into new positions. Now ask a basic question. Can you always run the machine backward? If someone gives you the output, can you recover exactly where it came from, using a rule that is just, clean as the original rule? That is only an analogy. The real conjecture is more precise. It concerns polynomial maps, transformations built from algebraic expressions with powers and coefficients. In that setting, the Jacobian is a way of measuring how the transformation behaves locally, near each point. Roughly speaking, it tells you whether the map is crushing space, folding it, or preserving enough information nearby that a local reverse process should exist. The Jacobian conjecture asks whether a strong kind of local reversibility forces global reversibility. In plain language, if this polynomial machine looks reversible in every tiny neighborhood, must the whole machine be reversible everywhere with a polynomial inverse? That sounds almost obvious, and that is part of the danger. Mathematics is filled with statements that feel true when you test small cases, true when you draw pictures, true when your intuition has no obvious place to object. But a conjecture is not a theorem. It is a claim waiting for proof or waiting for a single construction that destroys it. This is why a genuine counterexample would matter so much. It would not mean mathematics collapses. Math does not break like software. The rest of algebra would not suddenly vanish, but it would mean that a belief that survived for generations had a hidden fault line. It would force mathematicians to re-examine methods, assumptions, and connected work built around the idea that the conjecture should be true. And because the object is so abstract, the drama is easy to miss. There is no exploding lab, no telescope image, no courtroom confession. There is only a transformation, a condition, and the locked door of reversibility. On one side is a map that seems to behave perfectly in every small region. On the other side is the question of whether the whole structure can be unlocked. That is why even a possible counterexample gets attention, not because it is automatically correct, not because an AI says so, but because one valid counterexample would be enough. Now we arrive at the object at the center of the storm, not a theorem, not a verified disproof, not even, responsibly speaking, a mathematical result yet. What AI may have produced or helped bring into focus is better described as a candidate counterexample, a suspicious construction that appears at first glance to press against the Jacobian conjecture. A proof is a chain of reasoning that shows a statement must be true. In mathematics, it is not enough for the chain to look elegant or feel convincing or resemble something an expert might write. Every link has to hold. A counterexample is different. It is one object, one construction, one specific case that shows a universal claim is false. If a conjecture says every machine of a certain kind can be reversed cleanly, a counterexample is a machine of kind that cannot be reversed in the required way. A candidate counterexample is more fragile. It is a possibility, a lead, a line on the blackboard with a warning light over it. It may satisfy the conditions. It may fail one of them. It may look impossible for 5 minutes, then collapse under exact calculation. Or, in the rarest and most dramatic case, it may survive. This is why the burden of proof is so high. A generated expression is not evidence by itself. A chatlog is not a proof. A confident explanation from an AI system is not a verdict. The object has to be checked exactly, with algebra that does not depend on mood, momentum, or the persuasive rhythm of a model's answer. That is what makes the recent public interest so strange. A video centered on Terry Tao's GPT chatlog about the Jacobian Conjecture became a signal flare for viewers following AI and mathematics. But the important point is not that a famous name appeared near an AI discussion, and it is not. A theorem was suddenly settled in public. The important point is that people could watch expert reasoning and machine-generated reasoning collide in a way that felt unusually close to the frontier. That collision is unsettling because AI systems are very good at producing mathematical language. They can imitate structure. They can suggest definitions. They can carry symbolic patterns across a page. Sometimes they can point toward a promising path, but they can also skip a hidden condition, invent a step that does not follow, bury a fatal error inside notation that looks serious from a distance. So the drama moves from the machine to the human check. That is why videos built around someone checking the Jacobian conjecture by hand caught attention. The viral spark may be the AI output, but the real suspense is slower and less flashy. Does the proposed map actually fit the setup? Does the Jacobian condition really hold? Does the claimed failure of reversibility survive when the terms are expanded, simplified, and tested without shortcuts? This is where mathematics becomes almost forensic. Every line is a possible crime scene. One misplaced assumption can change the story from possible breakthrough to ordinary hallucination. One overlooked simplification can turn a dramatic counterexample into nothing. And yet the reverse is also true. If a suspicious construction survives exact checking, if every condition holds and the expected inverse really fails in the required way, then the story stops being internet curiosity and becomes something far larger. For now, the responsible language is careful. The claim is disputed or unverified. The object is a candidate, not a conclusion. The excitement is real, but excitement is not proof. So why does this feel different now? Why does a possible AI-linked construction around the Jacobian conjecture travel further than an ordinary math curiosity, even when the evidence is still uncertain? One reason is cultural. Recent AI math videos have started showing breakout behavior. That does not mean the mathematics is correct. It does not mean a conjecture has fallen. It means viewers are paying attention when AI appears to enter expert territory, especially when the territory is supposed to be narrow, technical, and hard to fake. For decades, advanced mathematics has been almost invisible to the general public. A proof can take years to understand. A counterexample can be a small object with enormous consequences. Most of the drama happens silently, inside notation, in the space between one line and the next. But AI changes the surface of that drama. Suddenly, a chatlog, a generated formula, or a strange algebraic construction can become a public event. People who may never read a research paper can still feel the tension. Did the machine find something, or did it merely imitate the shape of discovery? That distinction matters. Breakout attention on YouTube is not mathematical validation. A video can be fascinating, viral, and completely separate from the truth of a theorem. High interest tells us that the story has emotional force. It does not tell us that the Jacobian conjecture has been proved or disproved. The serious question is why the story has emotional force at all. Part of the answer is that modern AI systems can now produce work that looks close enough to expert reasoning to demand a second look. They can generate symbolic structures. They can suggest possible search paths. They can restate definitions, imitate proof strategies, and assemble long chains of algebraic language. Sometimes that is useful. Sometimes it is noise wearing the costume of precision. And in mathematics, that costume can be dangerous. A model can skip a condition. It can smuggle in an assumption. It can write an expression that appears coherent until someone expands it carefully. It can be almost right in a way that is worse than being obviously wrong, because an obvious error is cheap to dismiss. An almost right construction asks for time. It asks for attention. It asks a human being to check line after line. This is why the Jacobian Conjecture episode sits inside a much larger AI moment. The broader conversation around AI has moved far beyond chatbots answering homework questions. People are talking about data centers, energy use, space-based computing, scientific automation, and high-profile technology interviews about where AI may be heading next. Those topics are not evidence for anything about the Jacobian conjecture. They do not make the candidate counterexample more likely to be true, but they do form the background noise of the era. On one side, there are vast buildings filled with servers, power systems, cooling infrastructure, and capital. On the other side, there is a quiet blackboard, a polynomial map, and a single question that still has to be checked exactly. The contrast is almost strange. The world is building industrial machinery for intelligence, but the verdict on this particular claim may still come down to whether one algebraic construction survives ordinary mathematical scrutiny. That is the real shift. The story is not simply hype against skepticism. It is not believers versus doubters. It is the emergence of a new workflow, still unstable, where AI can generate leads that are interesting enough to test, not trustworthy enough to accept. Here is what can be said carefully. It is a fact that a viral AI math claim is not a proof. It is a theory that AI may help search through mathematical possibilities faster than humans can on their own. It is speculation that future systems may become stronger collaborators in discovery, not by replacing proof, but by changing where people look first. And that brings us to the most important part of the story. If AI is neither a magic mathematician nor just a random text generator, then where exactly does human judgment enter the loop? It enters at the hand check. This is where the story becomes much slower and much more interesting, because in mathematics, a shocking output is not an event by itself. A screenshot is not a proof. A confident explanation is not a proof. A construction that looks sophisticated is not a proof. Every symbol has to survive contact with exact checking. If the AI or an AI-assisted conversation points toward a possible counterexample to the Jacobian conjecture, the next step is not celebration, it is suspicion. The equation has to be copied carefully. The assumptions have to be identified. The map has to be tested against the actual setup of the problem, and every shortcut that might feel harmless has to be treated as a possible hiding place for the mistake. This is why the verification process has so much narrative power. It turns an abstract claim into a forensic investigation. Instead of asking in a vague way whether AI is brilliant or broken, the question becomes painfully specific. Does this candidate object actually belong to the class of polynomial transformations the conjecture is about? Does it satisfy the required Jacobian condition? And if it is supposed to be a counterexample, does the proposed reversibility fail in exactly the way it needs to fail? Those questions may sound technical, but the principle is simple. Imagine someone says they have found a locked door that proves an old rule about keys is false. First, you check whether it is really the kind of door the rule was talking about. Then you check whether the key behaves the way the claim says it behaves. Then you check whether the door truly cannot be opened or whether someone merely stopped turning the key too soon. In this story, that is the emotional center, not the viral spark, not the dramatic headline. The center is the slow process of trying to find out whether one suspicious construction is real, broken, or almost real in a dangerous way. And almost real may be the most unsettling category. AI systems can be wrong in obvious ways, but those errors are easy to discard. The harder cases are outputs that are structured, plausible, and close enough to serious mathematics that they demand time from serious people. A single false step in a dense calculation can make a candidate collapse, but finding that false step may take hours or days because the error is buried inside notation that looks purposeful. So the hand check is not a minor afterthought, it is the entire trial. The AI suggestion enters the room as a suspect object. Human verification interrogates it line by line. If the candidate satisfies the setup, the room gets quieter. If the Jacobian condition holds, quieter still. If the alleged failure of the inverse also survives, then the story changes shape. But if one part breaks, the claim does not become a breakthrough. It becomes evidence of something else. It shows how convincing a wrong mathematical object can look when generated by a machine trained to produce patterns of expert reasoning. And if the candidate fails, the episode still leaves behind a bigger question. Did AI fail randomly, or did it fail in a way that teaches mathematicians where to search next? That may be the real reason this story refuses to disappear. Not because the responsible answer is dramatic, but because the unresolved part is dramatic. It forces two uncomfortable ideas to stand side by side. The first idea is caution. AI systems can hallucinate. They can produce confident nonsense. They can create the impression of a proof without the substance of one. In mathematics, where one invalid step can destroy an entire argument, that weakness is not small, it is fundamental. The second idea is possibility. Even a flawed output can sometimes contain a useful pattern. A failed construction can point toward a nearby construction worth checking. A wrong proof can expose where a system is searching, what kinds of structures it finds natural, which regions of a problem space might be worth a human's time. That does not mean every AI math claim deserves attention. Most probably do not. It also does not mean the Jacobian conjecture has been cracked. The keyword demand around this topic is thin, and the evidence in the public conversation is limited. The responsible posture is modest and exploratory, but the fascination is understandable. A 90-year problem sits on the board. A machine produces or participates in a suspicious mathematical lead. People begin checking it by hand. Somewhere between the hype and the dismissal, a new kind of workflow appears. The machine does not need to understand mathematics the way a mathematician does to generate a candidate, but the candidate does need mathematics to survive. That is the dividing line. AI can suggest the door. It cannot declare the door locked. It can produce the map. It cannot decide, by style alone, that the map overturns a conjecture. The final authority is still proof. So, did AI crack the 90-year problem? The responsible answer is no, not from what can be verified here. A real counterexample to the Jacobian conjecture would not become true because it looks strange or because it spreads quickly. Because a chatbot arranged symbols in a convincing way, it would have to survive the same old test mathematics has always demanded: exact definitions, exact calculation, exact proof. That boundary matters. Viral momentum can make a claim feel bigger than it is. AI can make a wrong idea feel fluent. A chatlog can feel like a discovery while still hiding a fatal gap. And a candidate counterexample can be fascinating without being correct. But that does not make the episode meaningless. The more interesting breakthrough may be quieter. AI has shown that it can create mathematical suspense before it creates verified mathematics. It can produce an object strange enough that people want to inspect it. It can point toward a corner of a problem space that may not have been the first place a human looked. It can generate leads, patterns, and possible failures that still need to be interrogated by people who know what the symbols actually require. That is not the same as replacing mathematicians. In some ways, it makes the human role sharper. The machine can suggest. The mathematician must ask whether the suggestion even satisfies the setup. The machine can produce a line of algebra. The mathematician must decide whether that line is legal. The machine can create the spark. Proof is still the fire that has to be built by hand. This is why the recent wave of AI math videos feels different, even with thin keyword demand and uncertain claims. People are not just watching for a solved theorem. They are watching the border between plausible output and real knowledge. They are watching to see whether the new tools can become partners in the hardest kinds of reasoning, whether they are simply getting better at sounding close. For now, the Jacobian conjecture still deserves caution. No claim that a 90-year mystery has fallen unless rigorous verification says so. What remains is a more careful invitation. Follow the claims, but follow the checking more closely. Do not cheer for the machine. Do not dismiss it on sight. Ask what survives contact with proof. The next AI math story may not arrive as a finished theorem. It may arrive as a suspicious line on a blackboard that nobody can ignore.